much, and thanks to the organizers for all the effort and sweat of setting up this wonderful workshop. So over the next half an hour, we shall be concerned with something we spent quite some time with recently, even though this is still work in progress to some extent, but still the situation that will emerge from this little insight just seems so nicely ironic that I thought it would still be a good choice. And the problem that we are going to revisit is the so-called Boson-Sampling problem. And while this has a lot to do with random matrices, as John so nicely introduced yesterday, at the beginning of all this is a quite different idea, namely the one of building a universal quantum computer that's for to solve problems believed to be intractable on classical computers. Now, in the meantime, we might have noticed that this is not such an easy enterprise after all. A statement that applies to any of the proposed architectures for actually building a quantum computer in the lab, say with architectures based on linear optics, trapped ions, or others. So again, to state the obvious, in any of these proposed architectures, the benchmarks are exceedingly high. Say in this so-called KLM scheme for linear optical quantum computing, so the idea of building a quantum computer based on single photon sources, linear optical circuits, detectors, and classical like measurement and processing of the data and conditioning based on that, one needs like about 10,000 beam splitters to achieve a single CNOT gate operating at the fault-tolerant threshold. To be fair, this can be reduced, in fact, by orders of magnitude by resorting to measurement-based schemes, but still the overhead seems quite daunting. So people were thinking, wait a minute. I mean, of course, it's a great idea to build a universal quantum computer, but maybe it's a good idea as a kind of milestone along the way to just build some quantum device that presumably outperforms classical computers. So that relates to the notion of quantum supremacy that John Preskill semi-jokingly put on his blog not too long ago. So just have something in the lab, to realize something in the lab that you cannot keep track of classically efficiently, no matter what. Or at least you should have good evidence that this is the case, that you have something in the lab that outperforms classical computers. Now there seem to be two hotly contested candidates for that. One is the so-called D-wave machine that we discussed last night over dinner. The other one is the so-called Boson-Sampling device, which is a kind of linear optical quantum computer, but a very simple one from an experimental perspective, namely you prepare bosons, you let them go through a linear optical multiport, and you detect them at the end of the day. So there's no complicated conditioning, post-processing, things that are beyond technological capabilities anyway, but just you let bosons run through a linear optical multiport. So more precisely, the problem goes as follows, that you think of preparing n bosons, so n photons in m modes. Then you send these bosons through a linear optical circuit, and this circuit is described by unitarily transforming one set of bosonic operators to a new set of bosonic operators. So this linear optical network is described by such a UM element. But it should be clear that this unitary is not acting in Hilbert space, but it's really transforming modes. So phi of u is the Hilbert space representation, so the metaplectic representation, if you want. So u is the input to this quantum algorithm. And at the end of the day, you just measure photon numbers, so you get some output pattern, which is just some word of non-negative integers that just give the number of bosons in the respective slot. So let's do the experiment as a thought experiment. So we have 4 photons coming in, and we let them run through the device, and what we get is, well, 0, 2, 1, 0, 0, 0, 0, 0, 1. Okay? We go again into the lab, we do the experiment again. Now we get 1, 1, 0, 0, 0, 1, 1, 0. It's random, boson sampling. So it's like a quantum Galton board. So what is the probability of getting a certain outcome in that device? Well, that's, of course, the entire twist to this. So the probability of getting a certain outcome, word S, is up to a prefect. That's also important. The permanent, so not the determinant, but the permanent of a submatrix of this unitary U, which is obtained by taking the first n rows of that matrix, and then as many columns as you have bosons in the respective output word. That's the probability of getting that outcome. Now we know that the permanent cannot be computed efficiently. That's a computationally hard problem. Permanent is is sharp P hard. But to be fair, to be able to classically simulate that device, you don't need to be able to compute the probabilities. You only need to be able to sample from that distribution, which is a different and presumably simpler task. Now, the point of boson sampling, however, and that's Scott's insight, is that this is still a computationally hard problem to sample from that distribution. So this is the non-technical way of putting it, but it still conceives the main message here. So the sampling from a distribution which is close in one norm to the true boson sampling distribution is computationally hard with high probability when the unitary U, which describes the linear optical network, is chosen from the Haar measure, and M, which is the number of modes, increases sufficiently fast with n the number of photons. So experimentalists were sitting there and were digesting this and thought, oh, wait a minute, this is great. So in order to have a device in the lab that presumably outperforms classical computers, you don't need to have like a KLM scheme, complicated linear optical circuit with conditioning measurements and so on, things that are anyway beyond present technology. But in a way, you only need to prepare bosons, send them through a multiport and detect a pattern, and then you presumably have done something that you cannot do classically efficiently. What is more, there was a quite exciting experimental development recently of realizing such multiports on chip with integrated optical devices where the modes are like waveguides on top of the chip, and you can really sketch them in with etching techniques like in Bristol, for example. These things are nicely done. So a number of leading quantum opticians went into the lab and performed quite beautiful experiments that achieved a huge publicity. There were like 2 science papers back to back. There were 2 Natures, 1 Nature Photonics paper, and about 1 million popular science articles covering that, showing these quite exciting experiments. But to be fair, I hope, the kind of discussion of that was also quite loud, and the claims were a little bit grand. People said, now we have devices in the lab that outperform classical computers, and people like argued that the Church-Turing thesis is underfed and so on. So quite like grand claims associated with this. Now the point of the rest of the talk is that there's a kind of a twist to the story, which still seems to be crucial to the problem, which has been quite overlooked so far. And the problem is quite basically, well, how would we know whether we know what we are doing, whether we are correct? Yeah, so this is not an NP problem. We don't have a witness to find out whether the outcome of the computation is the right thing. We just go into the lab, we get samples, so we have to judge based on the samples alone whether what we have is the right thing or whether the machine that we have in the lab is doing what we think it is doing. So that's a crucial question of certification, and that's in a way at the heart of the problem, as we will see. Which brings us to the technical part of the talk. I'm giving kind of the flavor of the proof. I don't have the time to go into the details, but I give a couple of hints as to where the argument goes. So what we are in is we want to certify black boxes as decision problems. We'd like to reach decisions from a number of samples of a given order in the natural system size of the sampling problem, which would here be the number of photons in the problem. We would say, like, if we accept in the good situations with a probability of 2/3 and reject with a probability of 2/3, we would say we can we can decide that problem from that order of samples, and if no such algorithm exists, then we say we cannot decide that from that order of samples. There's a number of variants of that question one can formulate that setting. What we are specifically interested in here is that we have some unknown distribution of the true device, like the P distribution of the boson sampler, and a known distribution Q which I will mention in a second, and we would like to find out, just from looking at samples alone, whether we have P, the right distribution, or Q, the other distribution. Now, at the beginning of this argument is a variant of the birthday paradox that obviously usually relates to the probability that among n randomly chosen people, 2 people have the same birthday on the same day, and the paradox being associated, this happens rather early on, like the probability is 1/2 at with as few as 26 people or so. So what we here need is kind of the converse statement, namely that the probability that L samples that are drawn from epsilon flat distributions are all different, where epsilon flat means that the highest probability occurring is epsilon, and clearly if the sample size is not too large and epsilon is rather small, then this probability is very high. The next concept we need is the one of a fingerprint matrix, which, roughly speaking, says everything that we can say by looking at samples alone, by just making ticks of what samples occur how many times. So the fingerprint matrix is the property of like pairs of samples of a certain length L, and like CAB would be the number of elements that appear exactly A times in the first sequence and B times in the second sequence. For example, if we have 2 sequences where one is like 1, 2, 3, 1, 1, and the other one is 2, 1, 3, 2, 1, then this here would be the fingerprint matrix associated with that. That's kind of everything you can say from samples that you can say in a permutation invariant fashion. There's always the trivial fingerprint matrix that is associated with the situation of no sampling appearing more than once. The point now is that if you have not too many samples, like L is of the order of 1 over epsilon to the power of 1/4, drawn from an epsilon flat distribution, then the probability of the fingerprint matrix not being the trivial matrix is small. It's of the order of the square root of epsilon of the given epsilon. And you might already be kind of guessing where this is heading at. Namely, the thing is that too few samples from epsilon flat distributions are just utterly useless. Maybe it's worth reading out this statement here. So if you have a distribution which is very flat, it's epsilon flat, and you have a deterministic decision algorithm A that takes samples of the black boxes as input testing in a permutation invariant property, is provided 1 over epsilon to the power of 1/4 many samples from each black box, then with a probability like very close to unity, like 1 minus 1 over the square root of epsilon, it outputs a constant value independent of the input. So it just spits out something that's not even related to what you put in. So if the distribution is very flat and you have too few samples from the distribution, there's no way any algorithm, no matter what you do, will spit out anything that has even information about the samples, but it will just output a value independent of the inputs that you put in. So few samples from flat distributions are useless. And the rest of the argument are just, well, this is actually the longest part of the paper. The rest of the argument is about showing in what way the distribution are epsilon flat with a small epsilon with very high probability. And this is an exercise in random matrix theory along the lines as John so nicely introduced yesterday. So one part of it is an argument that submatrices of unitary matrices look up to a rescaling like Gaussian IID matrices. There's a long tradition of that type of statement in random matrix theory. John mentioned that briefly yesterday. Here we need a specifically tight bound of that sort, like with a multiplicative error bound of the sort that you draw a Herr-Measure random unitary, and you want to know in what sense the subsystems, the submatrices that go into the permanent later look like Gaussian IID matrices. And the rest of the argument is an exercise in like large deviation bounds of Gaussian measures to show that if you draw a Herr-Measure random unitary, you look at the submatrices that enter the permanent in the distribution. You find that they look like Gaussian unitaries. You do this kind of large deviation bound exercise, and you found that with overwhelming probability, the distribution of this boson sampling problem is epsilon flat with a very small epsilon.
How is smaller?
Sorry?
How is smaller?
Oh, here, it's like the probability of this being like exponentially small in n. N is the photon number, so this is the epsilon that goes into here. So it's kind of with high probability exponentially small in the system size when you draw over Haar measure random unitaries. Okay, so let's take a deep breath and put everything together. So what does that mean? So we go into the lab and have this like boson sampling machine sitting there in the lab. We draw Haar measure random unitaries, we implement them, and we see what comes out at the end of the day in this device. So the resulting statement is that for a Haar random unitary U, it is with probability supra-exponentially close to 1 in n, impossible to decide, no matter what you do, from polynomially many samples, whether a given black box samples from the boson sampling distribution or the uniform one. Yeah? So in other words, you go into the lab, there's a person doing this boson sampling device, like with this $1 million machine, sitting there. You kind of etch the integrated circuits, you get the distribution out. Then an undergrad student comes in, like programs like for 3 minutes with 2 lines of MATLAB code that spits out the random uniform distribution, and there's no way, by looking at the samples alone, you can distinguish the output distribution from this $1 million device, or I'm guessing, well, it seems a reasonable order of magnitude, or like this 2 lines of MATLAB code that the undergrad student has kind of programmed in a minute. So no matter what you do from polynomial many samples, these distributions look just practically the same. Yes?
The experiments, they're done for finite values of n, right? So
yeah.
Does your result say something there? I mean, I presume, I don't know what their n is, but you say polynomially many samples. In March, I mean, because you're saying the experiments are not meaningful, but the experiments have a certain n equals 16 or something.
Indeed. That's a good question. I have a slide on that. Can I answer the question like 2 slides from now? Because that's a perfectly meaningful question. Like here, asymptotically, like you look at these samples and they would just look the same. This is the main insight. So in a way, you can kind of classically efficiently simulate the device. Like what is a kind of classical simulation? If A cannot be operationally distinguished from B, then A simulates that's B in every respect. So the thing is that operationally, from just looking at polynomial samples alone, distribution looks just like the uniform distribution. So in other words, that gives rise to a rather ironic situation that yes, it may be true that to approximate the true boson sampling distribution in one norm is computationally hard, yet at the same time, it's true that one can perfectly classically efficiently simulate that distribution by just spitting out uniform random numbers, and there's no way you can distinguish the former from the latter. So there's not a contradiction, yet like in this sense, one can just perfectly classically efficiently simulate the boson sampling device with a random number generator. Yes?
When you when they're close in one norm, when 2 distributions are close in one norm, doesn't that mean operationally that you could get your bias in guessing which one you had was, isn't your bias basically the one norm distance between the control distributions? So I don't quite understand. But what I'm saying is, if you can't tell this distribution from the uniform one, shouldn't they be really close in one norm?
No, this is not. No, this is not the same thing. This is like.
Isn't that information theoretic? Like, for example, imagine the. No.
Like one is about like the other one is like about like one norm closing. The other one is about sampling complexity as kind of with a symmetric algorithm of distinguishing one from the other. Yeah, I mean this is not a contradiction. We can be close in one norm, or you can be epsilon different in one norm, yet at the same time, from polynomially many samples alone, you cannot tell one apart from the other. And that's kind of that's the point. That's kind of the operational thing. It's not a contradiction, but I mean, the meaningful say of what, like, when I simulate you, if I look like you and I talk like you and I do everything like you, then I mean, am I you in a way, right? So the question is there any means of distinguishing one from the other? That seems the meaningful notion of I can A simulates B, and in this sense, there's no way you can tell them apart. And well, it's maybe right that approximating one norm may be hard, yet from just judging at the samples alone, you cannot tell them apart. So this is kind of the important. Yeah.
Sorry, but there's no computational bound here. Is that correct?
Okay. Well, this is about sampling complexities. You ask how many samples do I need in order to judge. Yeah. And in this sense, you have the ironic situation, I said it many times, that it may be hard to kind of approximate in one norm, but you cannot tell them apart. Okay.
Well, that's query complexity bound, right?
Indeed.
And one thing is that. So to answer him, so for example, if the one norm was really the measure here, and then pseudo-random generators couldn't exist. What's a pseudo-random generator? It's a very small subset of strings of 2 to the n.
But look, so pseudo-random generators, there is a computational bound. This one does not have a computational bound.
But he doesn't need so, because
I come to that in a minute.
But see, I am confused because I thought the one norm was given one sample from the distribution and your chance of guessing.
I think you can relate it to one norm. Maybe this is what you were just saying, which is it's the one norm of the k samples. Like if you look at the k sample distribution, those will be close in one norm, right?
So these are about one norm distances of distributions, right? So the claim is, of course, like also the hardest claim of Scott means you draw harm measure random unitaries, and then under the conjectures that given that are not proven, like the hardness of the Gaussian permanent, conjecture, then you cannot approximate. You cannot build a device that approximates the output distribution in one norm. That's the precise claim. Yeah, this is not a contradiction, but still one could argue that.
That samples from the distribution, and the difference between the distribution that you get and could be far in one norm.
Exactly. Yeah.
But I think then shouldn't it be easy with just one sample to guess which was which?
No, it's only far conditioned on the unitary. So the way it works is you draw a random unitary, which is your linear optical circuit. Conditioned on that unitary, the resulting distribution is far away in one norm.
I see. Okay, so that's the difference here.
But then, if you look at the k sample distribution, and one of them is just like k uniform draws, and the other one is like sample one unitary that you use for all k samples. And so those classical probability distributions are close in one norm as long as k is less than polynomial n, right? Is that?
Yeah, that's exactly true. That's great. I had very few slides, but that's good because there's already so many questions in the talk, so I'm almost there. So I said what I said, right? I mean, you go to the lab, the output distribution cannot be distinguished from polynomial samples by looking at samples alone. As a question on sampling complexity, you cannot distinguish the output distribution. That's a serious challenge to this Boson-Sampling program. So it may be true that it's hard, but yet from looking at the samples alone, you cannot judge the distribution that's presumably hard and doing something interesting, outperforming classical computers, yet that looks for practical purposes by looking at samples alone, like the uniform distribution. So that's the main thing I wanted to say. So I have 23 minutes. We had lots of questions already. So maybe as a kind of outlook, I add a couple of, bad news and some good news. So as I said, by sampling alone, not using information about the unitary, one cannot distinguish the device from a simple uniform random number generator. So are there any ways out? The one thing one could argue that is that whether like noise in experiments might help, right? I mean, of course, you do an experiment. If you want to simulate that device in the lab, you do not want to simulate the perfect distribution, but rather the one that is generated by the device in the lab. So there would be errors. Question: if you have high kind of reasons of errors, does that make the problem easier or harder in a way? And here, the point is that if you have very large errors, then by doing appropriate Wigner function sampling, one can even do an efficient simulation in the one norm. So then you can really say everything classically efficiently. That's not good. So this is surely not a way out. Is there hope? I don't know. I just give a couple of candidates. Like there's one chapter in the paper. What one could do, of course, is the other extreme by making use of full information about the unitary and make a huge list. Robert also discussed that. Make a huge list of all outcomes, and with exponential computing power, you compute all the probabilities of each of these respective outcomes. You make a huge table, and you know everything about the distribution based on the unitary. And then you can ask, based on that information, can you do better in sampling complexity by distinguishing one from the other if they are epsilon apart in one norm? That's kind of the state discrimination setting, that's like in this relative entropy setting. And indeed, it turns out that then you can, from polynomially many samples, judge one apart from the other. But that's, of course, unreasonable because, I mean, in order to do that, you need like exponential computing power to do it, and then you can sample. But if you have like exponential computing power in your lab, then maybe you have better things to do than to think about the boson sampling in the first place. That, I think, relates to your question on the computing power. So that's a bit of a trade-off, but that's an unreasonable trade-off. But there might be hope, although I'm not really seeing how that could be, but in principle it's conceivable that one uses like partial information about the unitary to lift the problem of sampling complexity somehow without having to compute the probabilities. I don't know, I mean, it seems unlikely for the very reason that it's hard to compute the outcomes of the probabilities for having to solve this sharp P problem, but that might be a way forward. And then there could be the perspective that one doesn't, I mean, the hardness claim of Scott makes use of Haar measure random unitaries, and so does our argument. But in principle, it would be conceivable of drawing like not Haar measure random unitaries, but K-designs, like from unitary K-designs, and then there could be space that it's still hard to sample from that, although it can help a little bit to distinguish the output distributions. Maybe. That is an open question. That might be an interesting way forward. And at the very end, you could say, okay, fine, can you certify some aspects of the circuit? Maybe you rip off the preparation, you rip off the detectors, and you just want to say whether your linear optical circuit in the middle is doing the right thing, right? And that's something you could ask, and this is something that is kind of work in progress, but you can do this to some extent, meaning that's kind of an interactive proof type system certification of a channel where you want to make random coherent inputs sampling and random measurements at the end, and using these random measurements and preparations, you want to get an estimate of the one-to-one norm closeness of the channel to the one that you anticipate you have. And this is exponentially better than tomography, but still not efficient in the system size. So it's not a solution, but for small system sizes, here that relates a bit to your question, one could say that I can check what I have in the lab is the right thing, at least for the circuit, and then you know what you have. That's good. But of course, then you put again the detector there and the preparation, and then you get a distribution out that again looks uniform random. So some of the irony is still there, but in principle, there are some aspects one can kind of think of certifying, even though not efficiently the system size, but for small scale systems like proof of principle, there would still be some room potentially. Which brings me to the end. I'm out of time. So we looked at linear optical computing, but not in this kind of KLM style, huge circuit, conditioned measurements, and post-processing thing, but in this kind of simple setting of just having a boson sampling device where you prepare photons and send them through a multiport and detect the pattern at the end of the day, which seems specifically interesting because there are claims that it's still hard to approximate the output distribution in a classical fashion. And yes, while it may well be true that you cannot efficiently approximate the output distribution in one norm, we found here that the output looks operationally indistinguishable from the uniform distribution from polynomially many samples. So what does it mean? Well, judge for yourself, but it surely means that if you go into the lab, you have the device that presumably outperforms classical computers. At the same time, you look at the output distribution, and that looks like the one that your undergrad student just spits out with 2 lines of MATLAB code. So that's the situation that is, and we hinted a bit at possible solutions that one may possibly cook up to, at least for small scale systems, kind of cure the situation. That brings me to the end of the talk, but I would like to end with a kind of higher authority than me to kind of sum that up, namely with Dilbert, who says that over here we have our random number generator, which says 9, 9, 9, 9, 9, 9, 9. Well, are we sure that's random? That's the problem with randomness. You can never be sure. Thanks a lot for your attention.
Are there more questions for Jens?
Yeah.
So, in your proof you mentioned that you use this black box scenario.
Yes.
Can you remind me what it takes exactly? I mean, this means that you don't know which unitary it is?
Exactly. That's kind of a symmetric algorithm. That's like the most general thing you can do by looking at the labels alone. Right? I mean, in a way that you can make any permutation of the labels, and any information you can extract from that would be the one that you can use. In this sense, the argument is true. That's kind of the black box set.
But in the Boson-Sampling theorem, you are given a specific unitary.
Indeed.
So
But that's the point. How would you use that? That's kind of the other extreme that I said. If you
they ask you, they give you they tell you classically, I want this unitary. Of course, then you may ask the question how to implement this, but there is a very specific unitary you are asked for.
That's absolutely true. But the point is that this will not help you, right? I mean, first of all, the complexity, the hardest claim is about drawing hard measure random unitaries, and then you have the hardest claim that you cannot approximate this in one norm efficiently. But then you are right. You go into the lab, you etch something in the lab, you have some specific unitary, you know the unitary. So one could, there's a reflex, and that's the reflex that you have. I know the unitary. Surely I would know, there would be a way of how to use that. And well, we have a way of how to use that, namely, you compute all the probabilities, and then you can hope to be better. That's kind of the state discrimination setting. But other than that, how would you use the information of the unitary? You have no way.
With very trivial examples where it's not a balanced outcome distribution just by building it up.
Well, sure. Well, yeah, good. But I mean, of course, like for very small settings, like if you have a two-mode beam splitter, it would be unbiased. Of course, there could be a bias, but that's not the point. Yeah, I mean, the point is that if you look at larger and larger systems, then you would draw a unitary, and the point is that there's no information you can use about the unitary that would help you in reducing the sample complexity. I mean, that might be a way out, but there's no way known of how to use that information about the unitary to reduce the sample complexity. So the only thing you can do is just looking at samples and judging, and the point is you cannot judge. See the point?
The basic catch is that if you could calculate what the output probabilities were supposed to be,
Exactly.
then you could just generate that probability distribution yourself.
Exactly.
Yeah,
Right? I mean,
but
Thank you.
you don't have, of course, you don't have access to the outcome probability distribution. Otherwise, you could do that. But
Exactly.
you still are not completely ignorant about the unitary. So there is something in the middle.
well, I mean, that's what I said, but maybe, maybe not. I mean, it's a hard problem. I mean, it's far from clear whether this intermediate regime exists. That's an open question, but
Okay.
the instinct is wrong that there's no way known, it's by far not clear, how would you use that information? Although it's somehow there, but the very hardness of the problem shows that you cannot make use of the probabilities because you cannot compute them. Right?
I don't want to use the priorities. I want to use just the unitary.
Yeah, but that's the, I mean,
Yeah.
that's the input to the algorithm. That's the point. You cannot do that.
Are there any more questions? Okay.
Thanks a lot for your interest.